Hi, welcome to my talk on online linear extractors for independent sources. My name is Zhiye. I'm a first-year PhD student in New York University, Shanghai, and this is a joint work I did with Yevgeniy Dodis, Siyao, known as Stephens-Davidowitz. The topic of this talk is randomness extraction, and the outline is the following. First of all, we'll discuss the randomness extraction model we're going to be working with in model description. Then we will see when our model gives a randomness extractor. More generally, we will consider the case when our model only gives a randomness condenser in the section of condenser result. And finally, I will give a proof sketch. Alright, let's start with model description. In this section, we are going to define online linear extractors. In fact, this model is a concretization of online extractors. So before we move on, we will first have a look at online extractors. As we all know, a randomness extractor is an algorithm that takes some weak random sources and outputs a nearly uniform distribution. It's a fundamental task in computer science. An online extractor is a deterministic algorithm with an n-bit state S that takes input sources one at a time and updates its state after each input. For example, S first takes x1, which is sampled from D1, updating itself, and S takes a second source x2, which is sampled from D2, updating itself, and so on. Online extractors capture the idea of gradually accumulating entropy from weak random sources. If the state is statistically close to uniform distribution after receiving finite samples, then this algorithm is a randomness extractor. If not, then this algorithm is a randomness condenser. We are interested in perhaps the simplest possible setting of online extractors, where input sources are independently sampled from the same entropic distribution. We call this concretized model as online linear extractors for independent sources. It's linear because the updating process, ext, is linear. To be more specific, suppose S is initially all zeros. X1 is a weak random source. S is updated by applying linear transformation A to S and then XOR with X1. In the slide, you can see that S0, the initial state, is updated to S1. Then we update S by applying A to S1 and XOR with X2 and so on. This process is repeated multiple times, and in the end, the final state is the output of online linear extractors. Before we move on, I just want to emphasize once again the setting of online linear extractors. First of all, the weak random sources we want to accumulate are modeled as RID samples from the same input distribution. Secondly, the mean entropy of the input distribution is lower bounded by k, where k is a non-zero number. This is the only restriction we impose on the input distribution. In other words, even if the input distribution is adversarial, as long as it satisfies the mean entropy requirement and the samples are independent, then online linear extractors can accumulate from this distribution. And finally, A is an n by n matrix which corresponds to a linear transformation over F2. In practice, Windows 10 used the online linear extractors as a key component of its random number generation infrastructure. For the 32-bit CPU, the state S is 32-bit long, and A is rotation by phi. A as a rotation will cyclically rotate a bit string by a constant. This is one of our motivations to study online linear extractors. I think the most important message about our model is that A characterizes an online linear extractors by the updating process. So we say A extracts if the output distribution is close to uniform distribution. More generally, we say A condenses from K bits to L bits if for any input distribution with K bits of entropy, the output converges to a distribution with L bits of entropy. Then we ask the following question. The first one is which matrices A are good extractors? A is a good extractor if A extracts from any input distribution with non-zero entropy within finite samples. That means starting from any distribution with non-zero entropy, we can always end up with a nearly uniform distribution. If A is a good extractor, we also want to know how many samples are needed. The second one is which matrices A are good condensers. A is a good condenser if A condenses from K bits to L bits within finite samples, where L is sufficiently larger than K. That means starting from weak random sources, we can end up with a distribution which is much more random than the input distribution. Our work has answered both of the questions, and we are going to present them one by one. Let's see the answer to the first question, which matrices A are good extractor. Remember that Windows 10 used the rotation as its matrix A, so is rotation a good extractor? Unfortunately, the answer is no. We notice that there is a natural obstruction that prevents A from extracting. Suppose A is rotation by 1, and the input distribution is uniform over all zeros and all ones. Remember that S is initially all zeros, so after the first update, S is all zeros with probability 1/2, and all ones with probability 1/2. So S is uniform over all zeros and all ones after the first update. It's not difficult to see that S remains uniform over all zeros and all ones after each update. So S stays in this little space and can't accumulate more than 1 bit of entropy. In this example, the vector space all zeros and all ones is called an invariant subspace of A. If you rotate all zeros by 1, it's all zeros. If you rotate all ones by 1, it's still all ones. If V is an invariant subspace of A, then for any vector in V, you apply A to this vector, then the resulting vector is still in V. Since all zeros and all ones is a common invariant subspace of rotations, we can see none of the rotations is an extractor because they fail to extract from distributions with mean entropy 1. And a good extractor needs to extract from any distribution with non-zero mean entropy. More generally, if A has a non-zero invariant subspace with dimension R, which is smaller than n, and the IID samples are from the uniform distribution over V, we can use the same reasoning to see S remains uniform over V after each update. In the end, S can never accumulate more than R bits of entropy, which means S cannot converge to uniform. We have shown invariant subspace is an obstruction that prevents A from extracting. We also proved it's actually the only obstruction. In other words, we proved that A is a good extractor, that is, S can converge to uniform for any input distribution with non-zero entropy. if and only if A has no non-trivial invariant subspace. As for the rate of convergence, we first notice that n over k is a sample lower bound. It means every single bit of entropy is accumulated into S without any loss. We also computed a sample upper bound for A. When n is small and the input distribution has mean entropy larger than 1, A extracts after relatively few samples. While the property of having a non-trivial invariant subspace might seem rather opaque, it's actually easy to check. Linear algebra tells us that A has no non-trivial invariant subspace if and only if its characteristic polynomial is irreducible. Additionally, there are very sparse matrices A having this property. For example, if A is a linear transformation corresponding to multiplication by a generator of the field F2 to n, while the first n-1 columns correspond to rotation by 1, and the last column corresponds to the coefficients of an n-degree irreducible polynomial, then this matrix has no non-trivial invariant subspace, and thus A is a good extractor. In practice, we can implement this A in time On since it corresponds to one shift and one conditional XOR with a fixed bit string. We also consider a more general question: which matrices A are good condensers? Recall that A is a good condenser means A accumulates randomness from an input distribution with k bits of entropy and outputs an distribution with L bits of entropy. L is sufficiently larger than k. So is rotation a good condenser? We continue the example of rotation by 1. We have seen A has invariant subspace V, which is all zeros and all ones. It has dimension 1. We denote the orthogonal component of V as U. U is a set of strings whose number of ones are even. It's easy to check that U is also an invariant subspace of A, and U has dimension n-1. If X is uniformly distributed over V, then S will get stuck in one bit of entropy. If X is uniformly distributed over U, then S will get stuck in n-1 bits of entropy. Of course, we don't want to get trapped in V, so we set k to be greater than 1 to avoid the uniform distribution over V. As for rotation by 1, the best we can hope for is to condense from any distribution with entropy greater than 1 to a distribution with at least n-1 bits of entropy. However, not every rotation by 1 has this property. Suppose, besides the common invariant subspace all zeros and all ones, A also has an invariant subspace with dimension 2, and then its orthogonal complement is also an invariant subspace of dimension n-2. We will have to increase k to be greater than 2 to avoid getting trapped in this small space, and meanwhile, we have to lower our expectations for the entropy accumulated. In our work, we proved rotation by 1 is indeed a good condenser, which can condense to n-1 bits of entropy, as long as n is a prime satisfying a number theoretical condition. Additionally, if n is the same spectral prime, and A becomes rotation by alpha, where alpha is coprime to n, A still condenses to n-1 bits. For general invertible matrices A, we proved if A transpose has a large irreducible invariant subspace, which means it can't be decomposed into a direct sum of smaller invariant subspaces, then A is a good condenser. In the case of rotation by 1, 1n is a special prime. The orthogonal complement of all zeros and all ones is an irreducible invariant subspace of dimension n-1. Now let's move on to the proof sketch. The condenser result used the same proof technique as the one used for extractor. So we will focus on the latter one, which is easier to understand. Although the extractor result is an if and only if statement, we will only need to prove one direction because the other one is obvious from counterexamples. Let's first see our proof techniques. After receiving m RID samples, we formally denote the distribution of S as ds. We want to compute the mean entropy of ds. If the mean entropy of ds is approximately n, then ds is close to uniform distribution. However, we can hardly compute the mean entropy from the probability mass function because the convolutional form is infeasible to compute. The Fourier coefficient arise naturally in our setting because they interact nicely with both convolution and the linear transformations. In the slide, dsw hat means the Fourier coefficients of ds at vector w. Since we use RID samples, each Fourier coefficient of the compound distribution ds can be decomposed into a product of multiple Fourier coefficients of input distribution d, which makes the computation feasible. So our goal is to compute the sum of the Fourier coefficients of ds at all vectors. Notice that the Fourier coefficient of any distribution at all zeros is always 1. We can safely ignore this string and compute the sum of Fourier coefficient of ds at non-zero vectors. If this sum is close to 0, then ds converges to uniform. In order to prove the extractor result, we first notice that if A has no non-trivial invariant subspace, then A transpose also has no non-trivial invariant subspace. Therefore, for any non-zero vector W, the set of n vectors generated by A transpose and W must be linearly independent. Otherwise, A transpose will have a non-trivial invariant subspace. If there are n-linearly independent vectors, our mean lemma tells us the product of their Fourier coefficients of D is upper bounded by a small constant. Recall that the Fourier coefficient of ds at a non-zero vector W after m RID samples is a product of m Fourier coefficients of D. We can divide this large product into small segments of consecutive products of length n. We can easily verify every segment is a product of Fourier coefficients of D at n-linearly independent vectors. So we can apply the mean lemma to every segment and then bound the Fourier coefficient of ds at W. Notice that individual Fourier coefficient of ds at any non-zero vector is exponentially small when m is sufficiently large. So the sum of Fourier coefficient at non-zero vector is close to 1, is close to 0 when the number of samples is sufficiently large. So by our previous discussion, ds is close to uniform, and this finishes the proof. Our mean lemma is also clean and interesting. it states that as long as there are n-linearly independent vectors, the product of their Fourier coefficients can be upper bounded by a constant, which depends on the mean entropy of the input distribution. To see how to get this upper bound, we first show the product of Fourier coefficients at n-linearly independent vectors is maximized when the input distribution is near uniform over the Hamming ball. By some property of this distribution, we can get the upper bound. To see what this distribution looks like, we first draw a Hamming ball, where each layer represents a set of strings with the same Hamming weight. We build this distribution up greedily. Since O0 has the largest Fourier coefficient, 1, we want to put more probability mass on strings whose number of ones is few, while maintaining mean entropy k. So obviously we put probability 2 minus k on O0 string, and then we put probability 2 minus k on vectors with Hamming weight 1, since they have the fewest non-zero coordinates, and then Hamming weight 2, and so on, until the total probability sums up to 1. In the slide, vectors in the blue shaded portion all have a probability 2 minus k, and all the other vectors have probability 0. If you reach the end of this talk, I just want to quickly recap what I've seen so far. So in the first few slides, we defined what is an online linear extractor, and showed it can be uniquely characterized by a matrix A. The structure of A, especially its invariant subspaces, determines the extractability or condensability of online linear extractors. More precisely, if A has no non-trivial invariant subspace, then it's a randomness extractor. If A is invertible and the A transpose has a large irreducible invariant subspace, then it's a good randomness condenser. This one closes my talk. Thanks for listening, and bye-bye.